Atul Kumar got his bachelor's degree from BHU and master's degree from IIT Madras, and now he's studying at IIT Madras. He will be talking about quantum entanglement.
So, in general, I would talk on some basic concepts related to quantum entanglement and information processing, which is part of my PhD work as well. So, I would like to start with reviewing the definition of quantum entanglement. To start, quantum entanglement is a quantum phenomena which characterized for two or more particles in a way that the properties or the state of one of the particle depends on the measurement outcome of the state of the other particle. For example, if we take a antisymmetric state corresponding to two particles represented here as psi 1 2 minus, here alpha I represent as spin up particle and beta as spin down particle. In case we try to measure the state of the second particle and the measurement outcome is beta 2, then the state of first particle is alpha 1, and in the other case, if the measurement outcome of second particle is alpha 2, the spin state of first particle is beta 1. That means that the spin state of first particle depends on the measurement outcome of the second particle, and we cannot define the exact pure state of any particles such that we cannot say that particle 1 is in alpha state or in beta state. So, in that sense these two particles are entangled. Another example that we can consider is a triplet state corresponding to two particles. From here on, I would represent spin up state as ket 0 and spin down state that is beta as ket 1. So, in quantum chemistry, what we use as ket 0 0 and 0 1 plus minus 1 0 and 1 1 as the 4 states, whereas in quantum computing we use 4 entangled states represented here as psi plus minus and phi plus minus, which obviously are called as Bell states and play a crucial role in any of the quantum information processing protocols. To take a counter example of entanglement, we could define this state where if we measure the state of first particle and found it in 0 1, the state of spin 2 is 0 plus 1 by root 2. In second case also, if the spin 1 is found in ket 1 state, the state of spin 2 is again the linear combination of 0 plus 1. That means that state of second particle does not depend on the measurement outcome of first spin. So, we can say that these two states are not entangled to each other, and in terms of a wave function representation, if we can show that these two states could be written, this state could be written as direct product of these two states, we say that these states are not entangled. Let me tell you now how this part of the project has been evolved as a research problem. I started my research by reading several articles on entanglement and the measures which has been associated with it. So, for two particle system, I found that there are concurrence, symmetry decomposition and entanglement of formation, which is based on the reduced density matrix of the subsystems. And for three particle systems, there was 3 tangle and average value of square of concurrence. Now, for the 3 tangle has been used for maximally entangled 3 particle state, and average value of square of the concurrence has been used for non-maximally entangled 3 particle states. So, what we thought is, why don't we give a criteria which could be applied to all sorts of particles, right, starting from 2 particle state to any arbitrary number of particles, and depending on any sort of entanglement which would be present. For that, we use particle correlations or correlation coefficients present between the particles. What it does, it gives a unique definition irrespective of the number of particles involved, and the correlation measures using correlation coefficients allow us to generalize the criteria for arbitrary number of particles. We have used this criteria in a systematic manner by taking standard examples from the literature, and to start with simple 2 particle systems, the correlation coefficients for 2 particle systems are defined in this way, where the components Cxx to Czz are represent the correlation between the 2 particles, and sigmas here are the Pauli spin matrices, and angular brackets represent the expectation value. To take the first standard example, we have used the Bell states and calculated the correlation coefficients, where the values of these correlation coefficients are listed here in this table. The value of correlation coefficients are shown to be maximum and plus minus 1, which obviously shows that the Bell states are maximally entangled to particle states. Coming to a 3-particle system, ZSZ state, the correlation coefficient listed here are shown the value as plus minus 1, which are maximum, shows that the 3-particle here show a maximal correlation between them. A 3-particle system such as this, which could be obtained by applying a Hadamard operation on second particle of ZSZ state, obviously is also shown to be maximally entangled here as shown by the correlation coefficients. For 3-particle W states which are non-maximally entangled state, the value of correlation coefficients is less than maximal, which shows that the correlation between 3 particles here is not maximum. The correlation coefficients for 4-particle systems are represented here. All these expressions have been obtained by solving the quantum cluster functions. To take first example, as a 4-particle ZSZ state, they show a the value of correlation coefficient is maximum, and for 4-particle entangled state proposed by Yuo and Chua in 2006, the correlation coefficients again show the maximum value, whereas for the 4-particle W state, the values of correlation coefficients are less than maximum, as represented here as 0.25. So, to summarize this part, whenever we find correlation coefficients value as 1 irrespective of the sign associated with that, we say that the state is maximally entangled, whereas whenever the correlation coefficients are less than maximum, the state is said to be less than maximally entangled state, and in case all the correlation coefficients are 0, that state is said to be product state or non-entangled state. That means there is no genuine correlation between the multiple particles. We have proposed with the existing norms such as concurrence, 3-tangle, and the average value of square of concurrence, and we have found that the value of correlation coefficients are in excellent agreement with concurrence. At the same time, for 3-particle, 4-particle, and 5-particle W states, the value of correlation coefficients are exact match of the average value of concurrence, and similar is the case with 3-tangle and value of correlation coefficients. So this accounts for the importance of this particular criteria. That means the criteria that we are proposing involves all sorts of entanglement present in a particular system, whether it's a 2-particle system, 3-particle system, whether it's a maximally entangled state or a non-maximally entangled state. It considers everything at the same time. So, and this is the expression for 4-particle correlation, 5-particle correlation coefficients, and based on all these expressions, we have proposed so many maximally entangled states to be used for quantum information processing in a way that the efficiency of information transfer could be increased. Coming on to the properties of the correlation coefficients that we have proposed, extent of correlation coefficient does not change with the change of particle indices. For example, if you take these 2 states, these are cluster states basically, psi 1, 2, 3, 4 or 5, 1, 2, 3, 4. 5, 1, 2, 3, 4 could be obtained from psi 1, 2, 3, 4 by changing the particle indices here from 1, 2 to 2, 1. So these 2 states possess 4 non-zero correlation coefficients which are maximum. At the same time, as I have already mentioned, if all the correlation coefficients associated with a particular state are 0, we say that the state is a product state and there is no genuine multi-particle correlation existing. For example, to take a state like this, which Rigolin has proposed in 2005 to teleport a 2-particle arbitrary state, we found that all the correlation coefficients associated with this state are 0. That means this state must be a direct product state, and in fact it is. That state could be written in this form, which shows that there is these are direct product state of 2 Bell states and there is no genuine 4-particle correlation existing. the extent of correlation between the particles remains invariant under the local unitary transformation, as already I have given an example of such type of states earlier in my talk, that which could be obtained by applying Hadamard operation on second particle. Now the degree of correlation between this is same as the 3 particle state in a ZZ. Now the most important thing which we deduce from this correlation coefficients is the way that we can distinguish different entangled systems. For example, if we calculate the correlation coefficients and number of non-zero correlation coefficients for 2 different states are not equal in number, then we say that those 2 entangled states belong to 2 different class of entangled systems. For example, if we consider here psi 1235 and phi 1235, the number of non-zero correlation coefficient associated with this particular state is 4, whereas with this particular state is 10. That means that this state doesn't belong to the same entangled class of state to which this state belongs. So we can differentiate these 2 entangled states in 2 different entangled class of systems. At the same time, if the number of correlation coefficients are same for 2 different states, then they may or may not belong to the same family of entangled systems. For example, if we consider these 3 states where state 1 and state 2 are kind of cluster type of states, and this state is a kite of state proposed by Yu and Chua, then we found that the non-zero correlation coefficient associated with all these 3 states are 4, but only these 2 states are related to each other by local transformations, which means that these 2 states belong to same family of states, whereas by doing no local transformation one could transform this particular state to either this or this, which says that chi type of state is a different class of state as compared to cluster type of states. And the most significant property of correlation coefficients comes in form of distinguishing 2 systems by doing local transformations. One way to do is to see all the local transformation that could be possible between 2 different states, or other way that we propose is to see the set of correlation coefficients, and by visual examination you would be able to know whether these 2 sets of correlation coefficients could be transformed into each other or not. For example, we take these 2 states, 4 particle states, and where the correlation coefficients for these 2 states are listed here. As you can see, this set of correlation coefficient could be transformed to this set of correlation coefficient by doing simple local transformations, where Hadamard transform, what it does is it takes x to z and z to x and leaves y as it is. So as the number of particle increases, also increases. So in that sense, it makes your job really hectic to see whether 2 set of states could be related through local transformation or not. But by calculating correlation coefficient and just doing visual transformation, you could see whether these 2 set of states could belong to same family or not. All these states that we have, some of the states that we have proposed, I am listing here, which have been used for applications in quantum information processing. To define quantum entanglement, it is a process in which information could be transferred from one remote location to another remote location without transferring the medium containing the quantum information and without doing any measurement on either side of the transport. So to take example, if there is a sender who has an unknown state represented here, and he or she wants to transfer this to a receiver, if let's say Alice and Bob, if she does any measurement on this state, it will either collapse to ket 0 with probability a square or ket 1 with probability v square. So the information would be lost. The way to do is that has been proposed by Bennett et al. In 1993 is quantum teleportation. I represent Alice and Bob here as cartoons from a Hindi movie, Hum and Tum, where, and we say that Alice and Bob share a quantum entangled channel represented here as I23 minus, where the particle 2 is with Alice and particle 3 is with Bob. Alice wants to teleport this particular state to Bob. For this, what she does is she just do on Bell basis in a way that Bob's particle would be identical to one of the state of first particle that Alice wanted to teleport in one of the state, that is psi 1 to minus. In all three cases, Bob has to do a single qubit unity transformation to recover the state. This is the algebraic detail associated with the algebra, which I am going to skip. Then for three particle system to be used as a entangled channel instead of a two particle Bell state, it has been found that in case we try to teleport a single particle state using a three particle ZSZ state, in 4 of the projections Bob could recover the unknown state, whereas in other 4 projections the information is lost if ZSZ basis is used as a projection basis. So the proposal that has been given by Carlson et al. Was controlled teleportation, where controller Charlie could assist Alice in transferring the information to Bob successfully. What we have proposed as an example is such type of quantum channel, which already I have mentioned in previous section. Such type of quantum channel, what happens is if we use ZSZ state as a quantum channel and this as a projection basis, or this as a quantum channel and ZSZ as a projection basis, in all the projections of Alice, the teleportation is feasible, and Bob would be able to recover the unknown state that has been teleported to him. So for multi-particle information transfer, one need a multi-particle quantum channel which could be either a direct product of Bell states or could be genuinely entangled multi-particle system. For this, such type of states, as I have mentioned, are set as chi type of state, and such type of states are said to be 4 particle cluster states and has been used for teleportation and other information processing applications. So what we do is we represent these channels in this form, and then generalize this channel for 2n number of particles in a way that maximum entanglement is always ensured. For example, we use these 4 particle states to theoretically construct a 6 particle state, and then 6 to 8 and so on. So in that process, the 2n particle entangled state corresponding to chi system could be represented in this form, where when n is equal to 2, this reduces down to this particular state. Now the sequential manner in which they are constructed ensures that entanglement properties of these states are preserved down to a pair of particles when they are symmetrically averaged. In a similar way, we have defined 5 particle quantum channels. To give one example, we represent a 5 particle entangled channel like this, where the states in these 2 columns are 3 particle ZSZ states represented here. This could be used to produce a 7 particle entangled channel and so on, in a way that we could define a 2n plus 1 particle maximally entangled quantum channel in this form. Yeah. As the number of particles increases, the number of ways that you could form this sort of maximally entangled states also increases. So this simple method gives you a way by which you can define several maximally entangled channels to be used for information processing. The question comes, why should we define such type of entangled channel? What is the need of that? So for multi-particle information processing, as I have mentioned, Rigolin has proposed a 4 particle entangled channel, which although do teleport a 2 particle information from sender to receiver, it doesn't have a 4 particle correlation between the particles. Similarly, Yuo and Chua have proposed a genuine 4-particle entangled state to accomplish the same task. However, at the end of the process, Bob has to do a 2-qubit transformation to recover the unknown state. A simple transformation of this state in this form could allow Bob to do a single qubit transformations. Instead of using this state, one can use this. 2008 Brown state has been used for teleportation, but here what they have shown is that the sender selects 16 particular projections out of 32. So in case of other 16 projections, the information is lost. So what we thought is we must found a way or to define teleportation such that the process is feasible in all the measurement outcomes done by the sender, and only single qubit unity transformation should be done on Bob's end. For this we have proposed several multi-particle entangled channels. Some of them I have represented here, and we have used it for direct as well as controlled teleportation. By saying direct teleportation, I mean there is only 2 parties involved and there is no intermediate controller involved in the process. To take one simple example, to teleport a 2-particle arbitrary state, we have used this quantum channel in a way that the projection basis that Alice could use could be represented in this form, where the exact projection basis could be obtained by applying Hadamard operation on 3rd particle of this particular basis. If Alice use such projection basis, the success is guaranteed, and Bob only has to do single qubit unity transformation instead of a joint qubit transformation. Similarly, a controlled teleportation has also been realized theoretically, where the particles are distributed between Alice, Charlie and Bob, and for this process to become successful, the basis that Alice must choose is chi type of state for 4-particle system, and a projection basis that Bob could use is represented here, Charlie could use is represented here. Now for theta is equal to pi by 4, that means the projection basis for Charlie is 0 plus minus 1 by root 2. The teleportation is successful, controlled teleportation is successful. So to summarize this section, we have constructed and characterized many multi-particle quantum channels theoretically for information processing, such that the process is feasible in all the measurements done by sender as well as controller, and the unity transformation that the sender has to do is only single qubit unity transformations. Coming on to the another application, that is quantum dense coding, which is one of the simplest application that utilizes quantum entanglement. Here if we consider Alice and Bob to share one of the entangled states represented here, such that qubit 1 is with Alice and qubit 2 is with Bob. If Alice wants to encode her message, she could use any of these 4 operators to map this particular Bell state to another Bell states in a way that she could produce 4 different messages for Bob. Once she encodes her message, she sends her qubit to Bob, who in turn does a Bell measurement on the joint state of 2 qubits to decode a message. Generalizing it for a 4-particle case, Alice has 16 different ways to encode her message, and the operator set that she could use is represented here. Once she encodes her message, she transfers her qubits to Bob, who does joint measurement on the state of 4 qubits to decode the message. For even number of particles, it is generalizable, and the efficiency of information is always 2 bits of information per qubit. However, the situation is not that simple for odd number of particles. For example, if we take a 3-particle ZZ state, then only 3 bit of information is transferred 2 qubits. So efficiency of information is 1.5 instead of 2. The table summarizes the transfer efficiency in case of controlled as well as direct process. 5-particle ZZ states or 5-particle W state has been used for quantum dense coding, and it has found that 4-bit information could be transferred using 3 bits of information. So here the information efficiency is 1.33 instead of 1.67, which could be in case of we are using a odd number of particles. We have used the quantum channels that we have proposed, and it has we shown that the operator set that Alice could use is represented here to encode her message, and by using these operator sets she could produce 32 different messages for Bob. So in that sense she could send 5 bit of information, which is maximum for a 5 particle entangled state. Alternatively, Alice could like dense coding could be realized in a controlled manner as well, where the particles are distributed between Alice, Charlie and Bob. So in that case, if Charlie measures his third particle represented here in this basis, then the quantum channel could be represented in this form. For theta is equal to pi by 4, the 4 particles are in maximally entangled system between Alice and Bob, and Alice could always send 4 bit of information by locally manipulating her 2 qubits. However, in general, Charlie could measure his particle in any basis, that is theta could be anything for him. For this particular purpose, we have given 2 particular schemes where Charlie could send his measurement outcome to both Alice or Bob. This is the first case where he sends his measurement outcome to Alice, and the second case is represented schematically here, where he sends his measurement outcome to Bob. Without going into the detailed algebra of the process, I would like to emphasize on the result that we have obtained. The amount of information transfer has been analyzed in terms of different analyzer angle that Charlie could use. So we have found that this graph gives you the amount of information transfer at different theta if one use 5 particle ZSZ state, whereas this shows the graph for chi or cluster type of states. But for some of the states that we have proposed, the information transfer, as you can see here, is always a maximum, irrespective of the what measurement basis Charlie uses. So in that sense, it gives a flexibility to the controller and in some sense to the experimental setup to use whatever projection basis or theta you want to use in case of a controller. This process has been generalized for 2n plus 1 particle system, and the average amount of information that could be transferred from a sender to receiver is found as 2 sin square theta plus 2n minus 1 if one uses cluster of chi type of state, whereas it is 2n in case one use the entangled state proposed by us. So and the other important result that has been obtained is that for multi-particle systems involving more than 5 particles, case 2 is more appealing due to further experimental convenience. Now, coming to teleportation and dense coding using non-maximally entangled states. When non-maximally entangled states such as W states have been used for teleporting a single particle, it has been found that the probability of teleportation depends on the coefficients of unknown states here represented as A and B. So what we have done is we have proposed different non-maximally entangled states. One such example was here, where the probability of teleportation has been found as this, and the total probability of teleportation was not unity, but it was depending on the unknown coefficients of the 2 particle system that we wanted to teleport. And second case where we have proposed a state like this, where the correlation coefficient for such a system are represented here, and the value of correlation coefficient is plus minus 1 by 2, which shows that there is a genuine 5 particle entanglement in such states. However, it is not maximum, but is more than what one obtains in case of 5 particle W state. At the same time, 5 particle W state could not be used for teleportation of a 2 particle information. So what we have shown here is we said that the state that we propose is distributed between Alice, Charlie and Bob, and first Charlie measures his particle in the basis represented here and then sends his measurement information to both Alice and Bob. Once Alice gets his measurement result, she does a measurement on her particles 1, 2, 3 and 4 in generalizable basis such that the unknown information is teleported to Bob, subject to the unitary transformation that he needed to do. In first case where the Charlie's measurement result is 0.7, the post measurement state is this, and the measurement basis that Alice has to use is generalizable basis. And in second case where the measurement outcome is Cat1, the post measurement state is represented here, and the measurement basis that Alice could use is this. The result is successful teleportation in all the measurement done by Alice and Charlie. For dense coding, we have used this 32 projections in a way that Alice should always be able to send 5 bit of information to Bob. So what happens is by using even non-maximally entangled state, we could transfer maximum amount of information from a sender to a receiver. And it should be noted that even by using maximally entangled state, one could transfer only 5 bit of information that we are getting here in case of non-maximally entangled states as well. So the conclusion of this part was like successful information processing is achieved using non-maximally entangled state with certainty in case of teleportation and with optimal information transfer in case of dense coding. The process obviously is generalizable. Now coming on to the density matrix application of some of the processes that we have seen in the previous slides. Professor Naresh has already discussed about the basic properties of density matrices, so I would just represent a 2-particle correlated density matrix in this form, where the correlation tensor is represented here, whose components represent the correlation between the particle 1 and 2. The unknown state that Alice wanted to teleport to Bob is represented here in this form, and the quantum channel which could be used between Alice and Bob is represented in operator form here. So depending on the preparation of the quantum channel and the measurement basis and the measurement used by Alice, we have calculated the 3-particle density matrix in case of the original scheme proposed by Bennett et al. And we have found that 3-particle density matrix could be represented in this form. Now the trace of 3-particle density matrix before and after the measurement that Alice has done has been preserved. So it can be seen that the total probability of teleportation depends on the polarization vector associated with the different components as well as the correlation coefficient associated with the 2-particle case. We have generalized it for a 3-particle system where the density matrix of 3-particle system could be represented in this form, and for controlled process proposed by Carlson et al. We have represented part of the density matrix here, where again you could see the probability of teleportation depends on polarization vector as well as the correlation coefficients. Similarly, for 3-particle double states also the final result shows that the probability of teleportation depends on the correlation coefficients and polarization vector. So by doing this, one could see the spatial decoherence in the system, and at the same time could relate the probability and fidelity of the process with respect to the statistics of the system. So to summarize the talk, we have proposed a measure of entanglement for multi-particle systems which could be generalized based on the particle correlation irrespective of the number of particles present or the type of entanglement present in the system. The properties of these correlation coefficients has been utilized to distinguish different entangled systems into different class and to see whether 2 sets of entangled systems could be transformed into each other by doing local transformations. The teleportation using maximally entangled states obviates the need of a controller involved in the process, and the control dense coding using the states that we have proposed always the information transfer using control dense coding is always a maximum irrespective of the measurement basis used by the controller. Teleportation using non-maximally entangled state is not probabilistic, and the total probability of unity total probability of teleportation is unity, and at the same time the amount of information transfer using dense coding is maximum. Density matrix approach is used to establish relation between statistical parameters and probability of the information processing. Thank you.
Are there any questions?
You are teleporting non-maximally entangled state.
Yeah,
so how does it make a difference in the result?
No, we are using non-maximally entangled state as a quantum channel. Okay, so what is the difference you are saying? Basically, what we thought initially is in terms of security, if the information is controlled by many agents in a process, there is more chances of information to be leaked. But if it is in between me and you, we could assure the security of the process. Like if I have to send some information to you, I could be assured that I am sending it to you and I am not depending on some intermediate agents present in the process. So that was the idea to start with.
So do we need to meet in physical before, do we need to meet in physical to communicate afterwards? There is no controller.
No. No, basically as soon as I send you a classical information over a classical channel, you will be able to know that what unitary transformation that you need to make or to decode the message that I have sent through.
One more question I want to ask, that you told about the classification of entangled system on the basis of correlation coefficients. What is the significance of this classification? You say number of correlation coefficient may be same, but they may not belong to same family.
Right.
So what is the significance of this class?
Significance in the sense you get a criteria where you don't have to worry about how many particles are involved. Once you solve the expression for quantum cluster functions, you could program and say like calculate the correlation coefficients and distinguish these states, whether it's a maximally entangled state, non-maximally entangled state or a product state. That is one part. Other thing what you are saying is it is important to distinguish, like for example suppose someone has proposed a state and published it. I am also proposing a state and I don't know whether it has already been in the literature or not. So in that sense you have to see whether the state that you are proposing could be locally transformed from that state or not. So these correlation coefficients help you to visualize whether the states are related through local unitary transformation or not, so that you can differentiate, okay, there is one class of entangled state, there is another class of entangled state, and there is another class of entangled state. For example, for 3-particle system, there are only 2 class of entangled systems, ZZ or W state, which could not be locally transformed into each other. So depending on that, for 4, 5, 6, 7 number of particles, you could just calculate the correlation coefficient, and depending on their properties, you could say whether one particular state depends belongs to this particular entangled set or this or this or that. Yes, sir. Yes, sir.
Multi-particle state, you can always talk about entanglement between any of the two or three qubits, right? I mean, say you take 2 of the qubits and then you talk about concurrence, for example. Right?
Yeah.
So in all these numbers which you have, is there anything that measures entanglement between any 2 qubits? Between any 2 qubits. If I was to ask what is the entanglement?
Yes, because just a second. Okay, I missed the correlation coefficient for 3-particle system.
Be nice if you can write a bit bigger. I can't.
Yeah.
Maybe you should write bigger. I can't read. Yeah, if you have a black, please use that.
So for example, if you take this particular formula, once you calculate different values of these sigmas, you come to know that what sort of entanglement is present, like two particle entanglement here. If you get the values of these, like these product states here, for example, you calculate all the sigmas for 3 particles, like 27 components, then 9 components for 3, and then whatever single particle statistics would be there. 3 particle statistics, 2 particle statistics, and single particle statistics you have to calculate to finally calculate what sort of correlation is present. So there you could see that 3 particle, what is the condition with 3 particle statistics, 2 particle statistics, and single particle statistics, and based on that you would be able to know that whether it's like 2 particle correlation, like in W state, 3 particle W states is a 2 particle correlation is present. So that you could visualize by calculating.
See, I don't actually see that. I mean, do you actually have a proof or something of that? Because if you take 2 of the qubits, they will be in a mixed state. And then the definition of entanglement of mixed states is that they cannot be represented as a convex sum of separable states. Now,
like for example,
if I take that and I take this, how do I connect these two?
One particular example I will show you, like for this state. This state, actually, this is a mixed state and it's not entangled. But if you calculate the correlation coefficients, the 9 correlation coefficients, you get a value of CZZ as 1. So according to the criteria, it should be a maximally entangled state, whereas it is not. But the problem is that this state is not pure, and a single correlation coefficient doesn't guarantee you that the state is maximally entangled. For this, there are 2 things. One, if you are getting one single correlation coefficient as non-zero and your state is pure, then it is guaranteed that maximum entanglement is there. In other case, there should be more than one non-zero correlation coefficients present. That means more than one statistical data should be present, non-zero statistical data should be present with you to ensure whether your state is having a genuine correlation between 2 particles or not.
Actually, there's a difference between correlation and entanglement. Are you saying that if you have more than 2...
Correlation is there, but this is a classical correlation. This is not a quantum correlation.
Yes, so I mean, if you have more than 2 C's which are non-zero, would you say that that is equivalent to an entangled density matrix?
Exactly. In case...
Is that a proof, or I mean, is that something
based on... Yes, there is a proof. There is a proof. In 2006, there was a paper in New Journal of Physics where they have shown this as a theorem that you should have purity of state along with one statistical data, or if the state is not pure, you should have more than one non-zero statistical data present along with you to ensure whether the state is genuinely entangled or not.
Thank you. Thank you.